There is an image that virtually every person on Earth carries in their head when they think about the expanding universe. I know this because I have asked audiences about it for 30 years in lecture halls and conference rooms and dinner conversations, and the image is almost always the same. The universe, in this mental picture, is a bubble or a balloon or an explosion. Something that started small and is growing larger, pushing outward into a surrounding space, expanding the way a soap bubble expands when you blow into it, the way an explosion expands when it detonates, the way a balloon expands when you fill it with air. The universe is something finite, contained, growing, and the space it is expanding into is the backdrop, the stage, the emptiness that was there before, and that the universe is gradually filling. I want to tell you that this image is wrong. Not approximately wrong. Not wrong in some minor technical sense that physicists care about, but that does not affect the basic picture. Wrong in the most fundamental way an image can be wrong, which is that every element of it misrepresents what is actually happening. The universe is not a bubble expanding into pre-existing space. Space itself is what is expanding. There is no surrounding emptiness that the universe is pushing into. There is no stage that predates the universe. There is no exterior. There is no outside. And when you ask, with genuine physical precision, what the expansion of the universe actually is, what it means for space itself to expand, what kind of thing space is when it expands, and most importantly, what, if anything, the universe is expanding into, you arrive at a question that physics has not fully answered. Not because physicists have not thought about it carefully, because the honest answer requires a mathematical framework that goes beyond the space and time we know, that does not have an adequate name in any human language, and that sits at the frontier of what our best theories can currently describe. The universe is expanding into something. We do not have a name for it yet. And the process of trying to find that name is, I think, one of the most important projects in fundamental physics. Let me build this carefully from the beginning, because the wrong image is so deeply embedded that dismantling it requires going back to first principles. Start with what expansion means. When astronomers say the universe is expanding, they mean that the distance between distant galaxies is increasing over time. Not that the galaxies are moving through space away from each other, the way cars move away from each other on a highway, but that the space between the galaxies is growing. New space is being created between them. The metric, the mathematical object that measures distances in space-time, is changing in such a way that separations between objects that are not gravitationally bound to each other are increasing. This distinction between galaxies moving through space and space itself growing is not a philosophical nicety. It has physical consequences. If galaxies were moving through space away from each other, their velocities would be limited by the speed of light. Nothing can move through space faster than light. But if space itself is expanding, there is no such limit. Distant regions of the universe can be receding from us faster than light, not because anything is moving through space faster than light, but because the space between us and those regions is growing so rapidly that the distance increases faster than light can traverse it. And this is exactly what we observe. The most distant galaxies we can detect are receding from us at several times the speed of light, not violating relativity, simply being carried away by the expansion of the space between us. So the expansion is not motion through a pre-existing space, it is the growth of space itself. The creation of more space where space already exists. Now here's the question I want you to sit with. What does it mean for space to grow? When space expands, what is it expanding into? The intuitive answer is that it must be expanding into something. Growth implies an increase in size. An increase in size implies that something that was smaller is now larger. Something that is larger than it was must occupy more of something than it did before. That something is what it is expanding into. This logic feels airtight. It is how growth works for everything we have ever directly observed. Balloons grow into air, fires grow into fuel, empires grow into territory. But here is where the physics of general relativity says something that directly contradicts this intuition. And understanding why requires understanding what space is in general relativity, which is quite different from what it is in everyday experience. In everyday experience, space is a container. It is the emptiness within which things exist and move. It has no intrinsic properties of its own. It is just there, passive, receptive, the stage on which the drama of matter and energy plays out. This conception of space, sometimes called absolute space, was formalized by Newton, and it served physics well for 2 centuries. Einstein's general relativity replaced it with something completely different. In general relativity, space is not a container. It is a dynamical entity. It has geometry. It curves. It bends. It warps in response to the matter and energy within it. The curvature of space-time is what we call gravity. The geometry of space-time tells matter how to move, and matter tells space-time how to curve. The relationship is dynamic, mutual, deeply coupled. Space-time is not a passive backdrop. It is an active participant in the physics. And crucially, the geometry of space-time in general relativity is intrinsic. It does not require an external space in which space-time is embedded in order to be defined. The curvature of space-time is a property of space-time itself, defined entirely by the relationships between points within space-time. There is no reference to anything outside. The mathematical object that describes space-time, the metric tensor, contains all the geometric information there is to contain, and that information is self-contained. It does not require a higher dimensional space in which the space-time sits for its definition. This is the key point, and I want to make it as concrete as I can with an analogy that I think captures the essential idea without distorting it too much. Consider the surface of the Earth. It is a 2-dimensional surface embedded in 3-dimensional space, and we are so familiar with that 3-dimensional space that it is hard to imagine the surface without it. But now imagine a being that lives entirely on the surface, a 2-dimensional creature that has no access to the 3rd dimension, no ability to perceive or measure anything off the surface. This being can still do geometry. It can measure distances along the surface. It can determine that the surface is curved, not flat, by noticing that the angles of triangles do not add up to 180 degrees, that parallel lines eventually meet, that the ratio of a circle's circumference to its diameter is less than pi. The being can characterize the geometry of the surface completely, using only measurements made within the surface. It does not need to refer to the 3-dimensional space in which the surface is embedded. The geometry is intrinsic. Now suppose this 2-dimensional world expands. Suppose the sphere gets larger, the way the surface of an inflating balloon gets larger. From the perspective of the 2-dimensional beings on the surface, distances between objects on the surface increase. The surface is expanding. But the expansion does not require the 2-dimensional beings to have any concept of the 3-dimensional space outside the surface. They can describe and measure the expansion entirely using intrinsic geometry. The fact that from our 3-dimensional perspective, the balloon is expanding into the surrounding air is a feature of the embedding, not of the intrinsic geometry. Our universe is analogous. General relativity describes it as a 4-dimensional space-time manifold with intrinsic geometry. The expansion of the universe is a feature of that intrinsic geometry. The scale factor, the mathematical object that describes how distances in the universe change over time, is part of the metric tensor of space-time, defined entirely within the space-time, requiring no external reference. The universe expanding does not require a higher dimensional space into which it expands. The expansion is intrinsic, self-contained, defined within the universe itself. This is why the question, what is the universe expanding into, is, from the perspective of general relativity, not well posed. General relativity does not recognize an exterior. The universe is a space-time manifold. It does not have an outside any more than the two-dimensional surface of the sphere has an outside, from the perspective of intrinsic two-dimensional geometry. But here is where the story gets interesting. And here is where I think the most honest answer to the question requires going beyond what general relativity currently says. General relativity is not the final theory. We know this because it breaks down at the Planck scale, at the smallest distances and highest energies, where quantum effects become important, and the classical description of space-time as a smooth continuum fails. We do not have a complete theory of quantum gravity, a theory that reconciles general relativity with quantum mechanics. And in the theories that attempt to provide that reconciliation, the picture of space-time changes in ways that make the question of what the universe is expanding into considerably more interesting. Let me tell you about string theory first, because it provides the most specific and concrete answer to this question, even if that answer is not proven. String theory, in its various formulations, is a theory of quantum gravity that requires more than 4 dimensions for its mathematical consistency. The original bosonic string theory required 26 dimensions. The superstring theories that dominated theoretical physics from the 1980s onward require 10 dimensions. M theory, the framework that unifies the different superstring theories, requires 11 dimensions. These extra dimensions are required by the mathematics. They are not added by hand to make things work. They follow from the structure of the theory. In the most widely studied versions of these theories, our universe is a 4-dimensional surface embedded in a higher dimensional space. The technical term is a brane, short for membrane, a generalization of the concept of a surface to higher dimensions. We live on a 4-dimensional brane embedded in a 10 or 11-dimensional bulk. The bulk is the higher dimensional space in which our brane exists. If this picture is correct, the answer to what is the universe expanding into has a specific answer. The universe, our brane, is expanding within the bulk. The bulk is the higher dimensional space. When our universe expands, it is growing in the directions of our familiar 3 spatial dimensions plus time, but these are directions within the brane. The bulk has additional directions that we cannot perceive or move in, because matter and the forces that make up our everyday experience, except gravity, are confined to the brane. We cannot see or measure the bulk directly. We experience only the 4-dimensional surface of the brane. From our perspective, inside the brane, the expansion of the universe looks exactly as general relativity describes it: intrinsic, self-contained, not requiring an external reference. But from the perspective of the bulk, if such a perspective existed, our universe would look like an expanding surface within a larger space. The expansion would have an exterior context. The something that the universe is expanding into would be the bulk. I want to be careful about what this means and what it does not mean. String theory is not proven. The brane picture is a theoretical framework that has enormous mathematical richness and that has produced some of the most important results in theoretical physics of the last 30 years, including the AD-CFT correspondence that resolved the black hole information paradox. But it has not been experimentally confirmed. We have no direct evidence that extra dimensions exist. We have no direct evidence that we live on a brane. The predictions of string theory that distinguish it from other theories remain, for the most part, untestable with current technology. What string theory does is provide a specific mathematical answer to the question of what the universe might be expanding into. The answer is a higher dimensional space whose geometry is determined by the equations of the theory. That space has its own structure, its own dynamics, its own properties. It is not nothing. It is not simply empty space of a familiar kind. It is a specific mathematical object defined by the equations of M-theory with specific numbers of dimensions, specific geometric relationships, specific physical consequences for the physics we observe on our brain. But string theory is not the only approach to quantum gravity, and the other approaches give different answers to the question of what space is at the most fundamental level. Let me tell you about the approach that I find most conceptually radical, because it gives an answer that is furthest from our intuitions about what space is and what expansion means. Loop quantum gravity, developed primarily by Lee Smolin and Carlo Rovelli and their collaborators starting in the 1980s, takes a different approach to quantizing gravity. Instead of embedding general relativity in a higher dimensional framework, loop quantum gravity quantizes the geometry of space-time directly. It treats the metric tensor, the mathematical object that describes space-time geometry, as a quantum field that obeys the rules of quantum mechanics. The result is a theory in which space-time itself has a quantum structure, in which space is not continuous, but is made of discrete quantum units, in which the concept of a smooth space-time manifold is an approximation valid at large scales, but breaking down at the Planck scale. In loop quantum gravity, space is made of discrete loops of quantum geometry, networks of quantum connections, whose statistical behavior gives rise to the familiar continuous space of large-scale physics. The expansion of the universe in this framework is the growth of these quantum networks, the addition of more discrete units of space to the network. There is no exterior space into which the universe expands. There is simply more quantum space-time, more nodes and links in the network, more of the fundamental discrete structure that constitutes space. What the universe is expanding into in this picture is more of itself, more quantum geometry, more discrete space-time, not into a pre-existing space, but through the addition of new discrete units of space-time to the existing structure. The expansion is the universe creating more of its own fundamental fabric. I find this picture genuinely beautiful and genuinely hard to visualize, because it requires abandoning the idea that space is a container in favor of the idea that space is a network of relationships. There is no inside and outside to a network. A network does not expand into anything. It grows by adding more nodes and connections. The universe, growing through the addition of more quantum space-time, is not expansion into something. It is a change in the topology and metric of the network of quantum geometry that constitutes space. But here is the question that neither string theory nor loop quantum gravity has fully answered, and that I think is the most important open question in the foundations of physics. What determines how space grows? What governs the rate at which new space-time is added to the network, or the rate at which our brain expands through the bulk? The answer in current cosmology is dark energy, the mysterious energy of the vacuum that is causing the expansion to accelerate. But dark energy is a description, not an explanation. It is a term in the equations that matches the observations without telling us what the physical process is. It tells us how the expansion is behaving without telling us why space grows at all. The rate at which the universe is expanding is not constant. In the very early universe, expansion was driven by the energy of the inflaton field, the hypothetical field responsible for cosmic inflation, and was extraordinarily rapid. After inflation ended, the expansion slowed, as the energy of the early universe was diluted by the expansion itself. For the first several billion years, the expansion continued to decelerate as the gravitational attraction of matter pulled back against it. Then, about 5 billion years ago, the expansion began to accelerate again, driven by dark energy. It has been accelerating ever since. The transition from deceleration to acceleration is one of the most important events in the history of the universe, and we do not understand it. We do not know what dark energy is. We do not know whether it is a genuine energy of the vacuum, a quantum field that permeates all space with a fixed energy density. We do not know whether it is a dynamical field that changes over time. We do not know whether it is an effect of extra dimensions, of modifications to general relativity at large scales, of quantum gravitational effects that become important on cosmological scales. The Hubble tension that I discussed in the very first video in this series, the discrepancy between the two independent measurements of the current expansion rate, may be a clue to the nature of dark energy and therefore to the nature of the expansion. If dark energy is not a fixed constant, but a dynamical field that has evolved over cosmic time, the Hubble tension might be explained. And if dark energy is dynamical, if the rate of expansion changes in ways that depend on the state of the dark energy field, then the question of what the universe is expanding into becomes even more complex. Because the expansion is then not a fixed feature of the universe's structure, but a dynamical process whose rate depends on the current state of a field we do not understand. I want to take you now to the most speculative but most important part of this conversation, the part where the physics runs out, and the question becomes a question not just about what we know, but about the limits of what we can know. General relativity is our most successful theory of gravity and space-time. It has passed every experimental test ever devised. But it is, we know, incomplete. It breaks down at singularities. It gives infinities at the Planck scale. It is incompatible with quantum mechanics in the regime where both are important. Whatever theory eventually replaces it or incorporates it as a limiting case will describe space-time differently, will describe space differently, will give a different answer to the question of what the universe is expanding into. The candidates we have, string theory and loop, quantum gravity and causal dynamical triangulations and asymptotic safety and others, each give a different answer. String theory says the universe expands within a higher dimensional bulk. Loop quantum gravity says space grows through the addition of discrete quantum units. Causal dynamical triangulations says space-time emerges from the statistical behavior of discrete four-dimensional simplices, the four-dimensional analogs of triangles whose collective behavior gives rise to continuous space-time at large scales. Each of these frameworks gives a different meaning to the word expansion and a different answer to the question of what the universe is expanding into. And the honest answer, the answer that I think physics is currently obligated to give, is that we do not know which of these frameworks is correct. We do not know what space is at the most fundamental level. We do not know what expansion means in that fundamental description. And we do not have a name for what the universe is expanding into because the framework that would give us that name is a framework we have not yet found. This is not a counsel of despair. It is a statement about where we are in the project of understanding the universe. Every revolution in physics has required the construction of new mathematical concepts that did not exist before the revolution. Calculus did not exist before Newton needed it for mechanics. Non-Euclidean geometry did not exist before Riemann needed it for what would become the mathematical foundation of general relativity. The concept of a Hilbert space did not exist before quantum mechanics needed it. Each of these mathematical structures was, before its invention, a thing without a name, a concept that physics needed but did not yet have. The concept of what space expands into, the mathematical description of the higher structure in which space-time exists or from which it emerges, is probably a similar case. It does not have a name because it does not yet have a complete mathematical description. The candidates we have, the bulk of string theory, the quantum spin networks of loop quantum gravity, the simplicial complexes of causal dynamical triangulations, are incomplete approximations to something we have not yet fully understood. The complete description, when it arrives, will require new mathematics, will introduce new concepts, will give a name to what does not yet have one. And here is what I find most extraordinary about this situation. The question of what the universe is expanding into is not a question about what is far away or what is unimaginably large. It is a question about what space is, about what the fabric of reality is made of, about the nature of the medium in which everything exists. You are in that medium right now. The space around you, the space between the atoms in your body, the space that your body occupies, is made of whatever kind of thing space turns out to be at the most fundamental level. The universe that you inhabit is the universe that is expanding. The something that it is expanding into, whatever that something turns out to be, is the context in which your entire existence occurs. You are not an observer of the expanding universe. You are part of the expanding universe. The space between the atoms of your body is subject to the same expansion that is separating the galaxies, though on the scale of your body. The gravitational and electromagnetic forces that bind atoms together dominate over the cosmological expansion and prevent it from operating at atomic scales. The space-time geometry that describes the universe's expansion is the same space-time geometry that describes the room you are in. You are inside the structure that is expanding. You are made of the fabric that is growing. Whatever the universe is expanding into, you are along for the journey. Not passively, not as a passenger in a vehicle, as part of the vehicle. A configuration of the expanding space-time that has become complex enough to ask questions about the expansion. A local structure in the growing network of quantum geometry, or a pattern on the expanding brane, or a specific arrangement of discrete space-time simplices, depending on which description turns out to be correct. In any case, you are not separate from the expansion, you are a part of it. And the something that the universe is expanding into is not somewhere else, far away, beyond the observable horizon. It is the context of your existence, the deeper structure of what space is, the thing that physics is slowly learning to name. There is something I want to say about the act of asking this question, because I think it matters. The question, what is the universe expanding into, is a question that arises directly from taking the best physics we have and pushing it to its limits. It is a question that general relativity raises by describing expansion as intrinsic to space-time without telling us what space-time is at the deepest level. It is a question that quantum gravity theories attempt to answer in different ways without any of them yet providing a complete answer. It is a question that is currently open, genuinely, in the strongest sense. Physicists who have spent their careers on this problem do not agree on the answer. The experiments and observations that would distinguish between the different proposals have not yet been performed, and some of them may not be performable with any technology we can currently imagine. But the question is not unanswerable in principle. It is a question about the structure of reality, and reality has a structure. Whatever that structure is, it is what it is, independently of our ability to describe it. The something that the universe is expanding into exists, or does not exist, as a fact about the physical world. And the project of finding out what it is, of developing the mathematics and the experiments and the theoretical frameworks needed to answer it, is among the most important things that physics is currently doing. I find that genuinely exciting. Not despite the uncertainty, because of it. The questions that are currently unanswerable are the questions that will define the next century of physics. They are the questions that will require new mathematics, new experiments, new conceptual frameworks, new names for things that currently have no names. They are the questions that will produce the next revolution in our understanding of what space is, what time is, what the universe is, and what it means for a configuration of matter within that universe to ask what the universe is expanding into. You are that configuration right now, asking that question. And the universe, whatever it is expanding into, is the context in which that remarkable thing is happening. Look up at the night sky. Every point of light you see is receding from you, carried away not by motion through space, but by the growth of space itself. The light you are seeing left those stars when the space between you and them was smaller than it is now, and by the time that light reaches your eyes, the stars themselves have moved still further away, carried by the continued expansion of the space between you. You are seeing the past of an expanding universe, looking out through space that has grown since the light that reaches your eyes began its journey. And underneath that expansion, beneath the metric that measures it and the equations that describe it and the dark energy that drives it, is a structure that physics has not yet fully characterized, a fabric whose fundamental nature is one of the deepest open questions in science. Space is not nothing. Space is something. The universe is not expanding into nothing. It is expanding into something. And the name for that something, when we finally find it, will be one of the most important words in the history of human understanding. If this changed the image in your head of what expansion means, if the universe looks different to you after this than it did before, I want to hear it in the comments. Tell me which of the frameworks, string theory's bulk, loop quantum gravities, quantum networks, something else entirely, feels most physically real to you and why. Tell me what you think we will find when we finally look closely enough at what space is made of. And subscribe if you want to keep going to the places where the physics runs out and the real questions begin.